All right. Thank you for watching this. This is being billed actually specifically as a rebuttal to Brian Greene's twin paradox resolution that he has as part of his World Science U courses that came out not too long ago. But it certainly is in no way, shape, or form an attack on Brian Greene or the course. I think the course as a whole, the courses as a whole are excellent. Whether you're already an expert in relativity or you're looking for an avenue to learn about relativity, or whether you endorse the theory lock, stock, and barrel, or whether you are skeptical of some pieces of the theory, I think it's the presentation is terrific, the visuals are terrific, the Q&A at the end of each segment is terrific. So overall, it's a great way to educate anyone on any level in a very simple, user-friendly way on a lot of the typical concepts in relativity, like relativity of simultaneity, length contraction, time dilation, and so on. The specific thing that I'm going to focus on for the most part is the twin paradox, and even that certainly isn't an attack on Greene, because you know, as you'll see, I would guess that the majority of the physics community would also endorse the resolution that he puts forth in the video. So there's a number of modules, over 40 or so modules, that I would encourage everybody to take a look at. Obviously, if you're watching this, hopefully you've watched it already, because if you're watching a video that's a rebuttal, hopefully you've actually seen the course first, so that you know what it is that I'm rebutting. If you haven't seen it, spoiler alert, the traveling twin is younger when he gets back, so sorry about that. But anyway, let's get going. So essentially, we're going to start out with the birth of the paradox, because you know, like I said, the twin paradox is something that's been you know, discussed since Einstein wrote his famous paper in 1905, introducing special relativity to the world. And in that, he made two postulates, which are right here. The first is Galileo's principle of relativity is to be preserved. All motion at constant velocity is to be considered relative, and the laws of physics for moving frames of reference are the same as the laws of physics that apply to stationary frames. And two, the velocity of light is to be considered constant regardless of the state of the motion of the light source. We're going to focus on one and really not talk about two, because where the paradox comes in is an additional statement that he makes in that same 1905 paper, which is if there are two stationary clocks at point A and point B, and the clocks are synchronized, and then the clock at point A moves to clock at point B at a certain velocity. Upon its arrival at point B, the clocks will no longer be in sync. The clock in motion A will be lagging behind the stationary clock B. So where the paradox arose was this statement here is very hard to reconcile with this third statement down here, because if all motion is considered constant velocity and there isn't a preferred reference frame, then how was it that A enjoyed a slower clock ticking from B's perspective, but not vice versa? So that is the birth of the paradox. And if really we have two choices, and I should say that, you know, I mean, a majority of the physics community, if you bring up the twin paradox, the responses will typically be, well, there really is no paradox. If you think there's a paradox, you just have a misunderstanding about the theory, or there's a piece of the puzzle that you're missing, or that you might be a conspiracy theorist, or there's a number of reasons out there why someone is led to believe that they think that there is still a paradox. But it really comes down to two choices here. If it's just a misunderstanding of some sort, then there will be a complete self-consistent explanation for how all three of those Einstein statements that we just saw can be true, and they can all work together. And in addition to that, all experimental evidence will agree with the entire theory and not conflict with any part of the twin paradox resolution. On the other hand, if the paradox is real, it will be demonstrated that all of the elements of the theories and its resolution cannot possibly be true based on one or more contradictions. And I really should say theories, because there's different segments to relativity in its entirety. There's special relativity, which is what Greene focuses on, including his twin paradox video, but there's also general relativity, and there's a principle of equivalence that's kind of a bridge point between the two. So in other words, if the theory is not self-consistent and there's contradictions, then game over. It doesn't necessarily mean all of relativity is wrong. before I go any further, I'll say that it certainly looks, from a physical evidence standpoint, that the phenomenon of time dilation is real. So I'm certainly not contesting that. But what we really need to do is take a close look at Einstein's explanation for why time dilates, and the twin paradox is a perfect exploitation of that, to see if Einstein's reasoning for why time dilates can in fact be possible. Physical evidence will disagree with at least one key element used to explain how all three of Einstein's statements are true if the paradox is real. So if one or both of these statements is true, then like it or not, we do have a paradox on our hands. Okay, so what's the official resolution? For a long time, anyone who challenged relativity would be thought to, again, be either misinformed or somebody who wants to take pot shots at Einstein or anything in between. And so we're all led to believe that the theory of relativity is something that's ironclad, and there really is no wiggle room. It's a slam dunk of a theory, and like it or not, it's tried, tested, true, and that's all there is to it. So you would think that if that were the case, there would be an official resolution that everybody is behind, and it's the same resolution that everybody's behind, and that physical evidence supports that, and everyone endorses it. In reality, though, there actually, and I'm talking about the mainstream physics community, there isn't one. There are actually many resolutions, and sometimes they actually conflict with one another, which is interesting. We can divide them into two main categories. The twin traveling with no acceleration during the trip, which would be within the realm of special relativity, and there are actually paradox resolutions, including Greene's, that stay within the confines of special relativity as a legitimate answer to how the traveling twin has a slower clock time upon unification than the stationary clock or the Earth clock. And then there's also resolutions which use acceleration and actually require that acceleration to solve the paradox. So it's interesting for a theory that's supposed to be a slam dunk, and there's a consensus that that there is no paradox whatsoever. The explanations for why there is no paradox are actually all over the place. Okay, and we will study Brian Greene's in detail, which because it's a special relativity video series that he did, a course that he did, he obviously focuses on no acceleration. I'll mention this probably again, but he does in some of his Q&A hint at using acceleration or general relativistic methods to also solve the paradox. He hints at it, refers to it, but since it was outside the scope of what he was doing, he didn't provide any examples for that. So maybe in the future he'll do something like that. Okay. So we will get into Greene's non-accelerating resolution, but just by comparison, we'll get into some other statements made by other physicists or scientists. And in this case, we'll start out with something that was published in Scientific American. I think it was reprinted a couple times, and one of the times that it was printed was in a 2003 Scientific American article. Scientific American has done a lot of articles on relativity, some on the twin paradox, and they basically put together an entire special series issue called Time. So this appears in that as well. But here's a statement. When the paradox is addressed, it is usually done so only briefly by saying that the one who feels the acceleration is the one who's younger at the end of the trip. While the result is correct, the explanation is misleading. Because of these types of incomplete explanations, to many partially informed people, the accelerations appear to be the issue. Therefore, it is believed that the general theory of relativity, which handles the acceleration mathematics of this, is required to explain the paradox. Of course, this conclusion is based on yet another mistake, since we don't need general relativity to handle the accelerations. The paradox can be unraveled by special relativity alone, and the accelerations incurred by the traveler are incidental. So clearly, here's something that appeared in Scientific American that will straighten us all out as to some of the potential confusion about how to solve the twin paradox. This person is saying that the general relativity, or using an induced gravity or a simulated gravity or a gravity equivalent in the way of an accelerating frame, is not necessary to solve the paradox, and therefore physically wouldn't necessarily have anything to do with why the traveling clock fell behind the earthbound clock, okay? So here is another example. Famous physicist John Wheeler wrote the book with Space-Time Physics with Edwin Taylor, very well-respected physicist for decades. I think he was an advisor to Richard Feynman. You know, he wrote a whole book on special relativity and included information on the twin paradox in that book. And in his twin paradox resolution, he poses the question, they pose the question, do we need general relativity? And they quickly answer no. They sum up the paradox by saying there's never any contradiction between a single clock in one frame and a single clock in any other frame. In this case, special relativity can do the job just fine, okay? So, you know, this is just a sample, a hodgepodge, but clearly if you do the research, you'll find an enormous amount of literature out there, both in scientific papers, in magazine articles, and books that will show resolutions to the twin paradox without the need for acceleration, because on a physical level it's claimed that it's not necessary or not needed. Well, what was Einstein's answer? I mean, he was the one who wrote the paper in 1905 that started this whole thing. So when questions arose as to whether this was a workable theory or not, he proposed a solution to this paradox. The actual comprehensive solution to the paradox didn't appear until 1918, but it kind of starts with principle of equivalence paper that he wrote in 1911. And he showed that the behaviors in a frame accelerating in outer space would match a non-moving frame in a gravitational field, which, you know, if you're familiar with the principle of equivalence, you already know what I'm talking about, but essentially, if I were in a motionless elevator car, and I walked in the elevator and pressed the buttons and I was waiting for the elevator to move here on Earth, obviously my feet would be held to the floor, I'd be feeling gravity. But if I were in outer space where there is no gravity, but the elevator were being accelerated, then the floor of that elevator box floating in outer space would be constantly meeting my feet. And if the force matched, I would feel like I was in a gravitational field. And so really those are Newtonian things, but Einstein then basically took another leap and said, well, there's going to be relativistic things that happen in both the accelerating frame and the gravitational frame that will match. So that's included in his principle of equivalence. And basically he's saying that the lower you are in a gravitational field, being on the floor of the elevator as opposed to the ceiling of the elevator, your clock will run slower on the floor of the elevator, and the clock will run faster on the ceiling of the elevator. So when you're in a higher gravitational potential, your clock will run faster. When you're in a lower gravitational potential, your clock will run slower. And with that, you will see respective blue shifting and red shifting of the light signals. So you could send light signals or even pulses, and if you were on the floor as the elevator were accelerating and pulses were being generated from the ceiling down to you, then you're accelerating to meet those pulses, and they will occur at a higher frequency. So you would see the clock on the ceiling running faster than yours. And if you were on the ceiling and pulses were being generated from the floor, then you're accelerating away from them, and the clock would appear to be running slower from your perspective up on the ceiling. So in this case, the shifting of the light signals matches what Einstein's proposing for how the clocks run differently at different positions of a gravitational field and in different positions of an accelerating frame. Okay. So if we look at Einstein's acceleration solution even more closely, we can divide the journey up into 5 steps. We could have the 2 twins on Earth, and then the twin would leave and accelerate to a certain velocity, travel at constant inertial velocity for a certain period of time. At some point, we'll decide to turn around. And you could do a real simple turnaround without direction change if you wanted to do that, where you could say, imagine an elevator car going in outer space, and it's got thrusters on both sides, so it's going linearly, and then it fires the thrusters when it wants to slow down and then turn around, and it doesn't go into a curve or turn around. It's just a simple linear out, linear back. But either way, we're still, the floor becomes the ceiling and vice versa. Either way, you're feeling gravity out here as you're turning around, and then you start to reaccelerate and then finally come home, okay? So what Einstein wrote about acceleration's role in the twin paradox is this. The traveling twin would have the clock phrased as U2 in this particular 1918 paper, and the earthbound twin who stays behind would have a clock called U1, okay? But remember, the whole point of the paradox was that Einstein's first postulate was that there is no preferred frame of reference. So where the conundrum came in was, well, boy, the clock that's moving can claim that they're stationary, and the clock that we had originally deemed stationary, why can't we say that that's moving past us? Well, Einstein actually says you can do that, so that's part of his solution. And when time slows down for the moving clock from the stationary guy's perspective, then time will also slow down for the other clock from the opposite clock's perspective. So it's called sometimes symmetrical or reciprocal time dilation, where when there's relative velocity and it's not accelerating and it's just inertial motion, then each participant can claim that the other clock is slowing down compared to their own. So he says during partial process 2 and 4, and keep in mind that 2 and 4 are the processes that are run inertially at constant velocity, and it's 3 that we're going to focus on for where the acceleration and the turnaround occurs, because you slow down and then speed back up again. Don't pay much attention to 1 and 5, and there's a reason for that. Might get into that, but anyway, partial processes 2 and 4 is where the two clocks are in relative motion. Okay. So what he says is during partial processes 2 and 4, the clock U1 going at velocity v runs indeed at a slower pace than resting clock U2. Again, in our pictorial model, it's actually U2 that's doing the traveling, but during that partial process 2 and 4, U2 can claim that it's still and that the Earth and everything is rushing either past it or away from it, depending. So it runs indeed slower pace than resting clock U2. However, this is more than compensated by a faster pace of U1 during a partial process 3, which again is the gravity of the turnaround. According to general theory of relativity, a clock will go faster the higher the gravitational potential of its location. During partial process 3, U1 is located at a higher gravitational potential than U2. Okay, and let's look at that a little more closely. Here's clock U1 back on Earth. Here's clock U2 that's actually engaging in the journey. But what he basically says is, well, in order for Galileo's principle to be preserved, we are going to put them on equal footing. So during this portion 2 and portion 4, they are on equal footing. There is going to be that reciprocal time dilation from the perspective of each. So U2 will see the U1 clock with a velocity going away, and then when we get to part 4, the U clock will be traveling with constant velocity back toward U2. So Einstein says it's okay to do that because that's postulate 1 in his 1905 theory. But what he says to resolve that is when the clocks eventually reunite and they both land back on Earth, it would be impossible for two clocks sitting next to each other in the same space to each continue to see the other one run more slowly. There has to be a difference that's agreed upon between the two, and it is this U2, this traveling clock, that will everyone will agree that it will have ticked off less time and will be younger or run slower than the U1 clock. And his explanation for that is sure, U2 will see U1 run slower also, but during this turnaround, U1 will speed up a whole bunch and more than compensate for that, so that when they reunite, U2 will definitely be younger or have ticked off less time. Okay. Max Born, also a Nobel Prize winner, did it. And the thing is there really isn't any mathematical treatment provided by Einstein in that 1918 paper. He just basically systematically lays it out step by step. He provides a few frames of reference, and next to each frame, step by step, he shows what each clock is going to be seeing during each segment, each process, 1 through 5. But he doesn't really provide any mathematics to show how or why the gravity portion, or the simulated gravity of the portion during that turnaround, is able to compensate for the apparent conundrum with the two clocks there. So Born does a relatively simple mathematical derivation that he includes in some of his writings, and he shows that yes, the when they reunite, there's going to be an agreement that the traveling clock will be running behind, but he does agree that during that relative velocity phase, that each of them will see the other clock running slower, and to undo that seeming paradox, it's all in the acceleration, okay? If you're new to the mathematics of this, just caution the special relativistic factor that's used to calculate the difference in how the clocks run is often approximated to something a little bit more simple, and Bohr, among many others, does that approximation when he's equating it to the gravity portion of that equation. But whether you see this or this, you can mathematically treat it to match it up against the acceleration portion. But Born says something very, very important when he's done with this. He says, the clock paradox is due to a false application of the special theory of relativity, namely to a case in which the methods of general theory should be applied. So it kind of flies in the face of some of the other things that we've seen, right? So it makes you wonder, what's going on here? The relativity is a solid theory, supposedly, as we are told by physicists all over the planet. And if you even question the statements made in Einstein's 1905 paper, because there's apparent contradiction, then you just have a misunderstanding of some sort, because there really is no paradox. And so because of that, you would then think that there is a consensus on the solution to that paradox, or what's happening to physically explain what's happening for those clocks when they reunite and how they got to where they got. But as you can see, we've got a hodgepodge of statements out there that some statements actually exclude the possibility of some of the other statements being true. So not everyone is definitely not in agreement on what's going on here. For additional endorsements of the acceleration model, also David Merman in his book, It's About Time, 2005, he also does a simple Born-like derivation. And Daniel Steyer, in the article American Journal of Physics, September 2007, does a much more long, detailed mathematical treatment of the journey, considering the math of the accelerating frame and the inertial portions of the trip. But whether you are looking at a simplified model or something a little bit more complex, you're essentially looking at the part of the theory, the mathematics that was born out of the principle of equivalence back in 1911, which is the gravitational potential, or the difference in gravitational potential, would be divided by the speed of light squared. And depending on the situation, the gravitational potential or difference in the gravitational potential could be calculated a number of different ways. If you're actually in a real gravitational field, a certain formula is used. If you're engaging in circular motion, there would be centripetal acceleration, which would cause a simulated gravity on the rotating frame. And for something simple like a linearly accelerating elevator box in outer space, then you would basically have the acceleration times the height of the difference between the two clocks, or sometimes GL is used, A for acceleration, G for gravity, which would be interchangeable, and H for height or L for length. So you'll see it characterized a number of different ways. So I'll use GL over C squared, which again is just going to be the difference in gravitational potential divided by the speed of light squared. And the higher you are in that gravitational potential, the faster your clock is going to run, and the lower you are in that gravitational potential, the slower your clock is going to run. All right. The interesting thing about this is it shows that there's not one but two separate mechanisms for time dilation. I'm not going to get into a real long, drawn-out thing about that, but I think that's a common thing that people miss when they're analyzing all the intricacies of relativity, because sometimes they'll say, well, you can basically just take the acceleration portion of a twin paradox journey and just use it like you would use special relativity, except just build in a rate of change there instead of it being constant velocity. Well, if you're looking at it from a special relativistic standpoint, then while you're engaging in constant velocity, then remember there's that reciprocal or symmetrical time dilation so that each sees the other's clock running slower. if you claim that acceleration is nothing more than what's happening during the special relativistic inertial portion, but just with a rate of change built in, then it would still be that symmetrical reciprocal time dilation enjoyed by each, but it's not. In this case, it's equal but opposite. In this case, the person or clock in the lower portion of that gravitational field or simulated gravity will be running slower, and the other one will be running higher. So it's equal but opposite instead of equal but the same. Okay. So again, we have Einstein's statement here, which is very important. Sometimes people will overlook the significance of his position on this. But during this constant velocity portion, both in process 2 and 4, the out and the back part of the journey, then the special relativistic factor would obviously be used to calculate how much the other clock slows down compared to its own, and that is kind of compensated for or completely undone by the gravitational or simulated gravitational factor, by which this clock will be running much faster and this clock will be running much slower. So the key to Einstein and Born and a lot of guys that follow that line of resolving the paradox will say the key is in the acceleration, and you can't resolve the paradox without the acceleration, which again is the total opposite of what a lot of other folks out there say. So is it a solid theory? The separate resolutions, often, one explanation for the paradox excludes the possibility of the other. And I should say this is a really important point that I want to make, because for some reason in relativity, and namely the twin paradox, a lot of times people will very easily accept that there's a number of ways to solve the paradox, or there's a bunch of variations out there. And it's true that there's a lot of different ways that all work out mathematically, for sure. That is not in dispute. But the question is what's really happening on a physical level, right? And there can only be one. Either in our universe, the acceleration is having an effect on those clocks and is the whole ball of wax, or it's not. So even though you can come up with different mathematical derivations to come up with the exact same result, and it would be the correct result, you can't say that all of them are happening. For example, if there was a police investigation, and part of the police investigation was how a person drove from point A to point B, I could prove mathematically that there's about 10 different routes that person could take. They could take the more direct route and go slower. They could take a more roundabout route and go faster and get there around the same time. I could come up with 10 different routes, no problem. But if it was a police investigation and the police were interested in gathering facts because this could be a criminal case and it's crucial as to what route that this person took when for an alibi or something, then they're going to look at eyewitness testimony. They're going to look at tire tracks. They're going to look at physical evidence and say, sure, there's a number of different ways that this person could have gone, but we're interested in what actually took place here, physically took place here. Same thing as biochemistry, for example. If I were working for a pharmaceutical company and I could have molecule A turning into molecule B in the human body, sure, I could say there's 7 different ways that A could convert to B. But there might be only one specific way that happens in the human body. There might be a certain set of enzymes that convert molecule A to molecule B. And if I worked for a pharmaceutical company, I sat back and said, well, boy, this is great. I've just shown 7 different ways that this could happen. That's only going to get you so far, because if the pharmaceutical company is interested in developing a drug to have an effect on that pathway, they want to know the actual physical single pathway that's taking place physically in the human body, as opposed to 7 different theories as to what could be happening. And I think people get caught up in how all of these different resolutions produce the correct result mathematically, and don't pay enough attention to, hey, look, let's try to analyze what's actually happening on a physical level. Okay. The other interesting thing here is that Einstein's own resolution to the paradox that he created in 1905 wasn't even, he didn't even have the resolution information until 2 years after he wrote the 1905 paper. So that's, that's interesting. I mean, if he had written those statements and it was a misunderstanding because somewhere else there was a 4th statement in that same paper that cleared up the confusion, then great. or maybe he'd written something in 1903 or 1904, then fine. But if he puts that information out there in 1905 and says there is no paradox and here's why, and he says it in 1918, but he uses stuff that he didn't develop until after the 1905 paper came out, then, you know, okay. The other thing that's interesting is I'm wondering why, and especially later, Einstein put out a lot of popular books, some very intensive with the mathematics, some with hardly any mathematics at all for the general reader. So there's a number of books out there. You know, with all that has been discussed on the twin paradox for decades, since 1905, I'm wondering why nowhere in here Einstein addresses the paradox. He talks about special relativity, general relativity, the principle of equivalence, relativity of rotating frames, but he doesn't even do a chapter on the twin paradox in any of these books, and maybe we'll get back to that. Interesting. Okay, so we're going to kind of now that we've seen a sample of some of the things that are out there, we'll maybe transition over to Brian Greene's resolution. And he does a very comprehensive, multiple explanation resolution of the twin paradox. In one or two of his videos, he uses a step-by-step space-time diagram, which has become pretty popular. Space-time diagrams kind of exploded after Einstein died, which is a kind of an interesting thing. And I don't believe Einstein used any space-time diagrams in resolving the paradox in any of his writings. I could be wrong about that, but I don't think he did. Which, if that's true, that's also pretty interesting. Because he obviously knew about the everything that Minkowski did and all the nuts and bolts that went into the whys and what fors of a space-time diagram. So, if he never saw the need to use that, where most people actually rely on it, But even though Greene uses a space-time diagram to discuss the twin paradox, I'm actually going to focus more on one of the better videos that Greene talks about with the twin paradox without acceleration, because he actually does a step-by-step mathematical account of what each clock is seeing. And that is absolutely excellent. Again, I don't agree with the resolution, but if you're trying to find out what relativity is, what the components of relativity are, and what the issues are with the paradox, there's some textbooks and even popular books that you can kind of get lost in. And the style that he presents this in, and with the visuals and the step-by-step is really, really, you can really see from each perspective, why and what for. Whether you agree with it or not, at least it's easy to comprehend how and why they arrived at the opinions that they did about this, okay? So we're going to get into a non-acceleration resolution of the twin paradox, and how most physicists do this is by using two travelers, so you have a grand total of 3 people and 3 clocks. And what happens is rather than traveler 1 stopping and turning around and creating some acceleration or gravity to deal with, they just transfer their clock information to a traveler who's coming in the other direction. And it's seamless because this traveler goes out to this particular point, which is called point P, and at the same time this person is buzzing by at that same slot, transfers the clock information, and then this person then is the one who reunites with the clock back on Earth. So this would be kind of like Einstein's U1, and this would be the U2 clock, and we'll keep calling it U2 throughout, even though there's one person here and another person here. I'm not going to get into U3, or any of you for that matter. So Greene uses the 3-person model to track the clock activity throughout the journey, and eliminating the need for acceleration. So some stats on this particular journey. The traveling clocks maintain a constant velocity of 92.3 approximately percent the speed of light, which he fractionally uses as 12/13ths the speed of light. For convenience sake, which is great, makes it easier to follow along. The Earth clock measures the entire trip to be 26 years, so the entire out and then the back. The Earth's clock, his stopwatch says 26 years after this green person crosses the finish line here. When the returning traveler passes Earth, her clock says she made the trip in 10 of her years, because it'd be 5 out, and then the clock information transfers, and then 5 back. So the clock for the traveler combined is running slower, which again works out with all of what relativity claims, so there's no problem there. And agrees that the Earth clock should have advanced 26 years during her 10-year time frame. Each person agrees that only 10 years should have elapsed for the traveler based on the readings and calculations. So what's the problem if everybody's in agreement here? Well, the problem is, in my opinion, the method that's used and quickly accepted. And that's just a small problem. I'm going to actually finish up with some physical evidence that's out there that really conflicts with a major part of the twin paradox resolution. So I'm going to finish with that. But anyway, I'm going to get into some of the more minor details here. In agreement with Einstein, the traveler agrees that during the inertial phase, the moving clock sees the Earth clock as running slower than its own. So this guy would be like the U2 and also seeing the U1 running slower, so that they could each see each other running slower, so nobody's on a preferred frame. All right, so no problem there, and that's obviously in agreement with Einstein's 1918 model. And remember, I said for the traveler, on their clocks, it says 5 years out and 5 years back, so that the traveler's clocks finish at 10 years total. So when the traveler gets to the halfway point, the traveler's clock reads 5 years, but since the traveler also sees the Earth clock as running slower, then it comes out to be slightly less than 2 years being ticked off the Earth clock from the perspective of the traveler. Greene shows that as 25 over 13 years, right? So that's how much time the Earth clock will elapse from the perspective of the moving clock when it has gotten to the halfway point, and 5 years will elapse on its own clock, and it gets to that point P, okay? But Greene says that at the, and I, again, this is a kind of standard procedure for a non-accelerating twin paradox resolution. So I say Greene says, but it certainly is, when we talk about relativity of simultaneity and changing frames, which we'll get into, I would dare say a majority of the physics community would have a resolution very much like this, if not identical, just not presented as clearly and as step-by-step as done in this video series here, okay? But what Greene says in this video is at this transfer point, the traveling clock will actually record 13 years having gone by instead of slightly less than 2 years. So you might say, well, how can that happen? And here's the explanation. In a previous video, Greene talks about entire grids of clocks that are synchronized and so on. But here it is in a nutshell. You've got a clock starting out on Earth as it's passing by Earth, and it syncs up with the Earth clock so that they can all read exactly 12 midnight on New Year's year 2033 or whatever, right? So this blue traveler back here at moment 1, or moment 0, is synced up with the Earth clock, and as it's traveling, it sees that the Earth clock is running slower than itself. When it gets to this transfer point, and a lot is discussed about changing frames when we go from one to another, and the relativity of simultaneity, meaning that we have to kind of change our perspective. But basically, what it is this: physicists will then elect to take a time duration of how much time would have ticked off a fixed clock at point P from the beginning point. So that's really, really important to understand. It's synced up with the Earth clock as it's going by Earth, and understands that the Earth clock is running slower as it's taking constant velocity outward. But then at that magic moment of the transfer, it decides it's going to record 13 years have gone by, because that's what it would have recorded a fixed clock out here at point P had it tracked how much time would have ticked off from the beginning of its journey. So it tacks on extra years, and now we're at 13 years. Now, and the other thing too is in the video, it talks about transferring the 5-year clock time from the outbound traveler to the inbound traveler. I would assume that Greene also means that it's transferring the clock times that it's keeping a record of the Earth clocks too, so that we have something to report by the time we get back to Earth. So assuming that the 13 years that it would have recorded is what's transferred over to this returning traveler, that's where we're at that point, okay? But then what this traveler does is, now we are in what a fixed clock would read at point P. Now this returning traveler, before it gets back, decides that it's also going to tack on 144 over 13. So the first 144 over 13 was from this one changing its perspective to P and what it would have read P at, even though it started out on equal footing with the Earth located clock. And then this guy decides he's going to change back to the Earth perspective because he's taken the transfer time from blue at what it would read at P, and then adds on that second 144 over 13 so it can readjust what it's going to read from here to here from the Earth clock's perspective. So you have to ask yourself at that point, is that okay with you? Do you have any issue with that? Do you have any problem with that? If you don't, then what would be your reason for finding that an acceptable solution to the paradox? If you do, you're not the only one, right? To me, I guess I would equate it to having $1,000 in the bank and taking out 500, putting 500 back in, taking out 500 and putting 500 back in a few times a day, and say, hey, I made a couple grand today, isn't that great? But all I did was just move money back and forth. I didn't really make anything. And so we've shifted which perspective we're going to look at and then shifted back. And what that does is that tacks on more time to advance the Earth clock from the perspective of this guy, again, without acceleration, completely in the special relativistic inertial frame, okay? But then finally, because we're not done yet, this traveling green clock coming back also recognizes that in addition to all of that from the simultaneity issues and the frame changing issues, that the actual clock itself will also be ticking off slower like the guys recognized on the outbound journey, or Gale, and that would add on another 25 over 13, or almost 2 years. So in reality, the grand total would be these from the outbound, and this including the perspective change, and these from the return journey, including its perspective change, add them all up, and you wind up getting 26 years, which is in agreement with what the clock should read. Again, completely without acceleration. Now, the interesting thing here is, if this were kind of put forward as a mathematical alternative, all right? If this were put forward as a mathematical alternative to say, hey, there's another way to solve this problem without gravity, just in case you don't feel like getting into the equations of gravity, but it's not really what's happening physically. It's just a way to do the math and figure out whose clock's going to be saying what at the end of the day. But I don't think that they're saying that. I think a lot of them out there say, in reality, you don't need acceleration to explain the twin paradox because of this frame changing and these simultaneity issues. So, a question then arises. Well, I'll get to that in a moment. Going to compare these frame changes to Einstein's original model. In Einstein's original model, in the 1918 model, even though he didn't provide any mathematics, he did put some frames in there and discuss step by step what's going to be happening in all 5 of those steps. And interesting from Einstein's perspective, and this goes back to Galileo, Newton, and Einstein. I mean, a frame is something that's kind of relative and arbitrary. Right now I can consider myself in a particular frame, or I can say I'm in a different frame. If I were on a train moving 30 miles an hour, I could say that I'm in the Earth frame and I'm moving 30 miles an hour, or I could say that I'm in the train's frame and I'm not moving at all. That's the beauty of all this. So the frame is something that it doesn't have a physical existence at all. So it's just something that you can arbitrarily decide which you are going to be in at that time. A little bit different than the language that's used when the non-accelerating twin paradox resolution is presented, because the non-accelerating twin paradox resolution almost makes it mandatory. Well, hey, you're going out, and before you come back, you are changing frames, like it or not, right? So we're kicking you off the bus and putting you on a different one. Definitely in conflict with what Einstein maps out, because if you are traveling in this K prime frame, then there's going to be periods of time where you are not going to be feeling anything during the inertial portion, and then there's going to be periods of time where you are going to be feeling gravity, but you're in the same frame the entire time. It's the K prime frame. Over here, if you're the person on Earth and you're in the K frame, then you're going to see the traveler engaging in acceleration from time to time, but you haven't changed frames during that entire time. So even though your circumstances can change during the journey, the frame that you're in can actually be the same the entire time, according to Einstein. So that's a big difference between the two, which definitely needs more discussion. So again, would a single traveling twin who experiences gravity during a quick turnaround also be considered to change frames, right? Because the frame change is almost an essential thing in the non-accelerating model. So I then pose the question, if there is just a reversal, an actual real physical reversal in the course of about 5 seconds, which no human would have to be on board because they wouldn't last. But if there's a 5-second reversal, 2.5 to slow down and then another 2.5 to reaccelerate, that's a very short time frame to do a complete direction change at a very high velocity. But during those 5 seconds, would the proponents of the theory that we just analyzed, would they consider there be a mandatory frame change there as well, even though there was a very tiny acceleration period there? Because if they consider the frame change as being mandatory, whether you're just transferring information, and that's another thing. I mean, you're just transferring information, so it really isn't a resolution to the twin paradox. You're just transferring information. It never fully explains what would happen if two twins were separated and one physically went out and one physically came back. But anyway, so if acceleration were experienced for a brief period of time, would the proponents of the non-accelerating mandatory frame changing theory still consider that person to have changed frames in 5 seconds as opposed to instantaneously with the clock information transfer? Because if they still considered a frame change in that very small turnaround period, well then, hey, well if the frame change actually causes differences in the clock, but also gravity occurs as well, now you've got two contributing factors, and what happens? Do you have double the compensation or not? So it's really a mess that needs to be sorted out so that we can really understand what's going on here step by step, right? What the two versions have in common. So if you look at the mandatory acceleration version proposed by Einstein and later explained by Bohr and a bunch of others, and you compare that to what seems to have really taken over, which is kind of like the space-time diagram, free of acceleration, explain the whole thing with special relativity, no problem. So those two main categories, there are obviously differences, I just pointed them out, but the big thing that they have in common is process 2 and process 4, which is the inertial portion or the constant velocity portion of that trip. There will be a symmetrical or reciprocal version viewing of the clocks slowing down for each, right, with that special relativistic factor, okay? So that's very, very important that at least that's two parts of the process that can be agreed on by most theories out there, okay? So since that is part of both theories, a question arises. During process 2 or process 4, when there's just constant relative velocity between them, can these two clocks be synchronized, right? According to relativity, each clock sees the other running slower than itself. So if, for example, if for every 60 minutes that ticks off U1's clock, it sees only 45 minutes tick on U2's clock because U2's is running slower from its perspective, then the reciprocal or symmetrical thing will happen. For every 60 minutes that U2 sees tick on its own clock, it will see only 45 minutes tick on U1. So they will each see the others run slowly, okay? That's important because if Galileo's principle is correct, and that's correct, those clocks, those two clocks that are in relative motion will never be able to be synchronized. Because if U1 slows his clock rate by 15 minutes per hour, then while the passing U2 clock ticks off 45 minutes, U1's clock will also tick off 45 minutes. Had the adjustment not been made, it would have been 60. He slows his clock rate down by 15, and now when this guy ticks off 45, U1's clock, even though in reality he knows 60 minutes has gone by because his watch tells him 60 minutes, but he's got the specially designed clock that he can adjust. U1's clock will have also ticked off 45 minutes. So from the perspective of U1, those clocks will be in sync, right? But from U2's perspective, after that adjustment is made by U1, U1 was already running slower than itself before U1 made the adjustment, right? It was already running slower. Now that U1 has mechanically slowed its clock, then U2 would actually see U1 run even slower. So essentially what's happening is if you make any adjustment to one clock so that you can sync it from that one perspective, you will actually throw it further out of whack from the other direction. So there's no adjustment that once you have reciprocal time dilation due to relative velocity, according to Einstein, as described in 1905 and endorsed from that point on in all of these twins paradox resolutions, if all of that is true, then it would be impossible to sync two clocks from both perspectives. Because like I said, if you adjust one to sync it up, that's great, but then from the other direction it sends it out of whack even more, okay? Why am I making a big deal out of this? Well, because we have atomic clocks all over the place in the GPS satellite system, okay? And we have satellite clocks that are orbiting the Earth with atomic clocks on them. We have ground control station clocks. We have receivers all over the place that are also receiving information from the satellites. So there's all kind of communication between both the satellite clocks and the clocks on Earth. So they actually use the atomic clocks to send very accurate time signatures to receiver clocks, and they also periodically receive updates and corrections from the ground control station clocks. There's several of them at various places around the Earth. And the clocks all obviously need to remain in sync in order to track receiver positions accurately, and it's a really big, huge deal. You know, it's done on the level of nanoseconds, and if they slip out of sync, then you have unacceptable inaccuracies. So they've really gone a long way to, with the technology to make all these compensations and make sure that the clocks are running in sync, because otherwise the receiver will take the wrong information and tell you that you're actually on the east side of town rather than the west, okay? Despite the fact that there is constant relative motion between all of these clocks, they remain in sync just fine. This relative velocity between the clocks demonstrates that there is no reciprocal time dilation between the satellites and the ground. So we have a problem because we have a physical system. We have floating evidence all over the place, all around us, that needs to be in sync, but yet if every aspect of Einstein's relativity is true, there's no way that this system would work at all, okay? So here's another perspective. You know, you've got clocks that are moving with the rotation of the Earth, and then at a different angle and at a different velocity, you've got the orbits of the GPS clock. So if we want to boldly say that the GPS is an example of why the entirety of relativity is incorrect, and by the way, again, it's actually an additional endorsement of time dilation. So that's an important component of Einstein's relativity. And this is actually just, you know, there's other things out there like the muon experiments, the Havell-Keating airplane atomic clock experiments, and on and on and on, particle accelerators. But this is a really good ongoing laboratory of atomic clocks, which really show that Einstein's prediction for time running differently, not only with velocity-related systems, but differences in gravitational potentials. This is a validation, a verification of that. So I certainly don't have any issue with that. But again, to me, the equally important issue isn't Einstein's claim of time dilation, because I think that's pretty solid. It's the explanation for how or why time dilates. The physical evidence certainly suggests that there's an issue with the explanation, according to the physics community, for why they think time dilates. So if we're going to say that this is evidence that there's something wrong with the theory, then I might try to disprove my rebuttal of the theory. And so I could bring up potential issues. What about the relativity of simultaneity? Well, with the relativity of simultaneity, a lot of theoretical examples are used. Like, for example, like if you've got high velocities, you could do mathematical examples where you could demonstrate or propose that because of the relative high velocities, the simultaneity issues would put a kink in your calculations, and certainly something that you couldn't ignore. Other examples where you might be traveling at a low velocity in a car, but comparing yourself to how the clocks tick one galaxy over. So even though your velocity is low, your distance is huge, and your simultaneity issues would have to be considered if you subscribe to all of that. The beauty of this is that the two systems of clocks, both in orbit and on Earth, are A, relatively low velocities, and B, relatively short distances. Simultaneity is actually something that's anticipated and compensated for. I think Greene calls it post-processing in some of his videos, where when you're registering clock times from one place to another, you can actually calculate positions from what the clock times were and where they came from, and therefore the distances that they had to travel. So simultaneity is actually something that's intentionally compensated for, and therefore completely separate from how the two clocks run with respect to another. So separate from simultaneity is the issue, hey, am I going to see your clock running faster than mine or slower, and if so, by how much? And the beauty of this setup is unlike some of the other examples I mentioned earlier, is this is the perfect model to separate simultaneity issues from the relative clock rates of the two systems, okay? Is this argument invalid because there's also time dilation due to non-inertial motion? It makes it more difficult to analyze, for sure, but it's definitely not invalid. I've had individuals occasionally say to me, well, you can't use this as an example because it's not an inertial frame, there's direction change, there's speed ups, there's slowdowns, and that sort of thing. Keep in mind that if you get into general relativistic or accelerated type time dilation, it does not shut off the special relativistic time dilation mechanism, for sure. A simple example of that is we're all in a gravitational field right now. So we're actually experiencing time dilation from gravity, from one method of dilating time, right? But if I were to start in motion on the surface of the Earth, separately we could calculate the special relativistic effects between you and I because of the relative motion that we have engaged in, separately from the fact that we're experiencing time dilation by being on the surface of the Earth. Okay, so it makes it more of a difficult analysis mathematically. But keep in mind, the bottom line is that there is constant relative motion between the two. This is not at the center of the Earth. These clocks are on the surface of the Earth, and they're rotating with a certain velocity. These, at a different angle and a different distance, are rotating with a completely different velocity. So you have a constant state of relative motion because you have constant ongoing distance changes between these rotating clocks and the Earth clocks. And anytime you have distance changes between two parties, you have relative motion, like it or not. Another proposal, well, can't we use the gravitational potential, or the difference in gravitational potential, where it's used for the centripetal acceleration of rotating frame, and offset the SR, special relativistic approximation for time dilation? So this would be the approximation that we saw in Born's calculation, and it can actually be equated to the gravitational potential, and therefore potential time dilation in a rotating frame? Well, the answer is absolutely not. You can come close if you're trying to use everything that Einstein wrote, and people after that also added to the mathematics, not only Born, but Wolfgang Pauli, and so on. You will find that this is actually used when comparing how clocks run based on difference in gravitational potential in a rotating frame, obviously because of the centripetal acceleration. But the problem there is that you would be comparing something at the center of the disk or the rotating frame to something somewhere further out. These clocks on Earth are neither in the center of the Earth nor are they motionless or traveling at the same angular velocity as the satellite clocks. They're actually at a different angle, traveling at the rotational velocity, which is completely different than the velocity of the satellite clock. So you absolutely have relative motion. That sounds crazy, doesn't it? You absolutely have relative motion between the two. And so there won't be there will be no way that you can offset. And the reason why I say offset is if I were someone out there trying to disprove what I'm telling you right now, then this might be my best shot, because I might say, you forgot about this, because then we could basically make that equal to the tangential velocity there, and then since that would then be the gravitational potential, and then we would substitute that in, and then substituting that in, we have c squared on the bottom of both, and then the 2 would go down below, and then this would be substituted in for that, which would then be the gravitational potential, and we could say, aha, what we think one speeds up for, the other one slows down, and then everybody's happy, everybody's in sync, but that's not the case. In this case, we can't escape the fact that we do have relative velocity between both parties. So what does it all mean? Well, it calls for a re-examination of Galileo's principle and suggests that time itself may be an emergent property from some fundamental behaviors. That's my opinion. I know there's others out there who have said something similar. And the interesting thing, I think, is that if you ask, do the behaviors of certain particles in systems, do they exist in time, or does all movement, activity, and behaviors of those things actually is that time? Is the expression of all of that actually time itself? And if you think the expression of all that is time itself, then already you're in conflict with special relativity, because then you're saying that time itself is a local effect to each system. Every atom out there is basically its own clock. When it engages in all of these fundamental behaviors, then it's its own clock. And if its time dilates when it's in a system like acceleration or high velocity or a gravitational field, then something is affecting or possibly impairing its ability to engage in those behaviors with the same efficiency. So time dilation may be an entirely local effect. High velocity acceleration or gravity may be interfering with how efficiently these fundamental behaviors can take place. So if we call into question Galileo's principle and say, well, hey, Galileo's principle shows that these two systems are on equal footing. So even though one accelerated, once we get past the point of acceleration and we show that there's relative velocity between the two, Einstein didn't care who it was that accelerated to begin with. When they're in that state, process 2 or process 4, they're each going to see the other's clock running slower, and the GPS system says otherwise, for sure. And so that calls into question Galileo's principle. Interestingly, though, even though you call into question Galileo's principle, it might be difficult to verify, because what's happening on an actual physical, local level to that system that's either accelerating or moving faster in gravity might be happening to everything in that system, and therefore hard to detect within that system. So the laws of physics might be different, but since they're different for everything in that system, they still might come out to be the same. So more time needs to be spent on this, I feel, and I'm hopeful that not just Greene with his future videos and future writings about this, I'm hopeful that the physics community actually spends more time analyzing the entirety of relativity, because if more time is spent on it, I think a better, more comprehensive theory of time could actually be developed, and that would be a nice side effect of that, because right now that seems to be the stumbling block in the entire physics community. We don't know what time it is. We can't agree on what time is. Does time really exist? Is it emergent property? Is it not? So there's all kinds of theories out there as to what time is, and I think the key is in the analysis of relativity, right? Because if we can really absolutely 100% be certain about what makes clocks speed up and slow down, then we might be able to determine what makes them run to begin with, right? So I think that the clues are in relativity, because time is affected with these relativistic concepts. So if we can figure that out, I think we'll go a long way. So anyway, food for thought, some things to think about, and hope you enjoyed this rebuttal. But again, certainly nothing personal. It was a great presentation of what most of the physics community tries to present, and that's that.